Hi, my name is Mohan Prakash. Today I am explaining about signals system. The subject is related to signals system. In this subject, I am taking a concept of analogy between vectors and signals, orthogon signal space, complexity orthogon signal space. So let's begin. Introduction to in this we talk about this all topics about in this video in the next I am explaining about all these topics in one by one. It starts with vector. A vector is a mathematically quality with a magnitude and direction. Vector can be added and scaled by a scalars. We can do dot product defines similarity and orthogonally vector perpendicular if do not product. Basic set of independent vectors that span a vector. Next, signals in vector. A signal x of t can be represented as a vector in infinite decimal in a dimensional space. So dimensional space operations. We can we can using this operation we can calculate the signals as a vector. Addition, scaling, and projection on addition, scaling, projection. Each signal corresponding to a point in a function space. This allows us to apply a linear algebra concepts to an analyst. Next, inner product for signals. Continuous case. X comma y is equal to integral x of t, y of t, dt over integral plus 1 comma plus 2. T1 comma T2, sorry, T1 comma T2. In discrete case, x comma y is equal to summation x of n summation x of n y of n. Defines similar measures between signals. Enables orthogonal and projections concepts in signal space. And next, analogy table. Vector space, signal space, vector signal, dot product to inner product, normal norm is length to signal energy or power, orthogonal to zero correlation, basic factor, basic signal, sinusoidal and polynomial. Dimensions numbers of an independent basic function. Next, orthogonality in vectors. U and V are orthogonal if U into V is equal to 0. Sorry, V into U is equal to 0. Implies they share no common components. Allowed decomposition of into perpendicular parts. Example 0, 1 comma 0 and 0 comma 1 mean 2 dimension means 2D. Basic of the vector decomposition orthogonality in sequence. Signal x of t and y of t are orthogonally. Integral x of t y of t dt is equal to 0 over the integral. Means the signal are independent and non-overlapping in energy. Example, sin omega t and cos omega t are orthogonal over Fourier period 0 to 2 pi. Orthogonal signals are key in communications or multiplexing. Orthogonal signal space. A set of mutual orthogonal signals G1, G2, so on Gn. Any signal x of t can be expressed as a linear combination of these basic signals. Orthogonality simplifies coefficient calculation, allows clear separation of signals in like analysis and transmission. Used in Fourier and Walsh and Calvert expressions. Orthogonal signal space. Orthonormal signal space. Orthonormal is equal to orthogonal plus each signal has unit form unit. The expression will be like this. Expansion coefficient Ck is equal to x comma gk. Simplifies calculation further. For example, a set of sinusoids normalized over an integral. Orthonormal basic ensure numerical stability and mathematical minimal restraints. Complex signals. Many signals in units are complex valued. Complex signal has a real and imaginary part. Example, x of t is equal to e power j omega naught t is equal to cos omega naught t plus I sin omega t. Sorry, this thing. X of t is equal to e power j omega t is equal to cos omega t plus I sin omega t. Usually, this analysis was complex, exponential, or mathematically permanent. Present oscillations, modulation, and phasor complexity complicated. Complex orthogonal. In product of complex signals, x of y x comma y is equal to integral x of t y into t dt. The orthogonality signal is an orthogonal if integral is equal to is 0. Means the signal has orthogonal if the integral is 0. Example e power j omega t and e power j omega t. For t are the orthogonal over a period of if omega not equal to omega dash. Conjugate ensures proper and energy measure and orthogonal conditions. Complexity orthogonal signal space. In a space spanned by mutual orthogonal complex signals. For Fourier basic functions, e power j in omega naught t are orthogonal and complex. Any periodic signal can be expressed as a sum of such exponential generalization of a real orthogonal signal space, foundation of a Fourier analysis in a signal decomposition. Here we see for Fourier basic functions, v dot j omega naught t are the orthogonal and complete. Any periodic signal can be expressed as a sum of each exponential. Generalization of a real and orthogonal signal space. Foundation of a Fourier's analysis and a signal decomposition. Next, applications. You see application signals represented in an orthogonal basic simplified storage. A signal is represented as an orthogonal basic simplified storage. Stacks a storage device. Fourier series and transformation decomposes signals into orthogonal concepts. Fourier series and transforms or decompose signals into orthogonal concepts. So it can decompose the signals into orthogonal concepts. Communication systems use orthogonal signals to avoid interference. Communication system can deviate these orthogonal signals and to avoid the interference. Data compression. Orthogonal basic reduce reductancy. Means the data will be uh, capable to the filtering orthogonal ideas is separating desired schematic from noise. The orthogonal adds any separation desired some of the noise signals. So the data the filtering are the most important in signals, orthogonal signals and vector signals. So next summary and conclusion. So vectors and signals are there share a strong analogy to inner products in orthogonality. So orthogonal signal space allows efficient respirations and analysis. Analysis means the signals one is efficient respiration and analysis. And the orthogonal basic simple pronunciation. Orthogonal complex orthogonal space between Fourier methods. So you can use this complex orthogonal space in between Fourier methods in various and different places. Applications so the signals are used in communications and comparison filtering modulations. Orthogonality and is equal to independence and efficiency in signals. So independence and efficiency is more important in the signals and how to accept it. And here the complex orthogonal space underpins Fourier methods. Applications, communication, comparison, filtering, and modification. So we can use in further there are some applications regarding to that complex and orthogonal signals. So I take a major applications of the vector signals and orthogonal signals and complex single space signals. So these are main applications of the signals. So these are main applications. Complex orthogonal space different Fourier methods. So Fourier method is also used in complex orthogonal spaces. So we can use different or yeah. Mhm. So yeah, the thank you.